as far as gases are concerned. So Monday's lecture was all about kind of setting the table for the calculations. So we went through and we talked about pressure. We did some pressure conversions in the video. We talked about some of the relationships that exist between pressure, volume, temperature, and amount of gas, the so-called gas laws. And you saw a number of these laws in action in lab last week. We're starting today's conversation by talking about what we call reference points. And the most common reference point that exists is something called STP, standard temperature and pressure. STP, standard temperature and pressure, represents a fixed point where we set the standards of the parameters for temperature and pressure. And those standards are 0 degrees Celsius, otherwise known as 273 Kelvin, and 1 atmosphere of pressure. Now, 1 atmosphere of pressure, again, using our conversions, we could think of this as 760 millimeters of mercury, or as 760 torr. Or any of the other units that are equivalent to atmospheres on that equivalency chart that is earlier in this presentation. Remember, for temperature we have to think of in absolute terms rather than in Celsius or relative terms. So Kelvin is what we are going to focus on there. And so 273 is the appropriate value for STP. Now, what this does for us is really important. What this really takes care of for us is this sets up one of our definitions of Avogadro's law. One mole of gas at STP is going to be equal to 22.4 liters of volume. This is one of the big things that Avogadro came up with. And this is ultimately, if you want to talk about the evolution of where Avogadro's number comes from, that 6.022 times 10 to the 23rd, a lot of his gas laws work ultimately kind of helped to fundamentalize what the fundamental unit for the mole was. And so what's really interesting about this is that this law applies regardless of the identity of the gas. So it doesn't matter if I have a really light gas like hydrogen or a really heavy gas like sulfur hexafluoride. If it is at STP and if I have 1 mole of it, it will take up 22.4 liters of space. And where that can be really useful for us is in doing things like density. Because we know that 1 mole of gas taking up 22.4 liters of space is going to have a certain mass to it. And we can derive that mass off of the periodic table. And we can take that mass and use that to figure out, okay, how many grams of this substance are going to be present in every liter. And that's all that gas density is. So there's one other thing that we can look at. This is called the combined gas law. Now, in each of the individual gas laws that we investigated last week in lab, Boyle's law, Charles' law, Gay-Lussac's law. All three of those assumed that the other parameters were being held constant. I assume that my pressure of gas and my amount of gas didn't change when I was looking at volume versus temperature. When I did that little experiment in the pipette with the colored water and how the colored water moved up and down based upon whether my pipette was in ice or in my hand or in room at temperature atmosphere or hot water, we assumed that the pressure inside was atmospheric. We assumed that the amount of gas inside of there was constant. And so I could investigate those two parameters directly and compare them directly. What the combined gas law takes into consideration is, what if that's not a possibility? What if pressure, volume, and temperature were all capable of changing all at the same time? Or an even wackier kind of circumstance, what if the amount of gas and all of those parameters were changing at the same time? Well, how it works is that we know that from Boyle's law, pressure and volume are inversely related, which means that P times V is going to give us some constant value. We know that for Charles' law, the volume divided by the temperature also gives us a constant value. From Avogadro's law, we know that the volume divided by the amount of gas gives us a constant value as well. Now, if all of these are present all at the same time, they all are going to end up equaling the same constant. And to that end, since they all equal out to the same constant, we can actually set the conditions equal to each other. And so that's where we end up getting this particular version of the combined gas law. P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. Now, we don't see this version of the combined gas law very often because it would require that the amount of gas is variable, meaning that in my vessel, somehow I have the ability to let gas out or let gas in as the reaction or as the physical process is proceeding. That's not usually what happens. This version of the combined gas law sometimes gets rearranged PV over NT is equal to R, and R representing that constant that they all are together equaling. This is referred to as the ideal gas law. Now, this is the only mention that we're going to make of the ideal gas law because most of the applications of the ideal gas law require some calculations of quantity that we really don't want to get into, and we really have no desire to get into for this course either. So more often than not, what we end up looking at is scenarios that are a lot more common, where I have a trapped gas, and in that trapped gas, I am going to change those three variables simultaneously. Imagine you've got a balloon, and you blow up the balloon, you tie it off, and you then take it and move it from in here to a freezer. Well, in that scenario, all three of those variables are going to change. Right now, it's at a very particular pressure, a very particular temperature, a very particular volume. You move it over into the freezer, we're going to see a drop in the temperature. We're going to see the balloon shrink, and we're probably going to see some sort of pressure decrease as a result as well. And for those scenarios, this is how we would end up calculating. P1 times V1 over T1 is equal to P2 times V2 over T2. This is what we refer to generally as the combined gas law. Our combined gas law has pressure, volume, and temperature all changing at the same time. Again, this is a deviation from the ideal gas law. The ideal gas law includes the amount of gas, N, as one of those changing variables as well. And again, we're not going to look at that because that involves more involved kinds of chemistry and chemical reactions than what we're interested in here. So let's do some examples and some practice with the calculation side here. A sample of oxygen is at a half atmosphere and occupies a volume of 10 liters at 0 degrees Celsius. What is the pressure of the gas if it is at 15 liters and 25 Celsius? So when we go into gas law problems like this, what we need to be able to do is we need to be able to identify the before and the after. Where are we starting and where are we going? And if we can do that, it makes using the equations easier because I know where things are. So our initial conditions are all right here. The half atmosphere, the 10 liters, and the 0 degrees Celsius. These are all going to be our ones. So that means that our P1 is going to be the half atmosphere. That means that our V1 is going to be the 10 liters. And that means that our T1 is going to be the 0 degrees Celsius, which again, we got to convert into Kelvin. 0 plus 273 gives me 273 Kelvin. So those are our one conditions. Our two conditions, well, this is what is changing. We've gone from 10 liters to 15. That's our V2. We've gone from 0 Celsius to 25. That's our T2. We're asked what is the pressure. So that must be our P2. We don't know what it is. We're going to have a variable that we need to solve for. So using the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. I can now start to put in my numbers. For P1, I had half an atmosphere, 0.500 ATM. For volume 1, I had 10.0 liters. For T1, I did the calculation already, 273 Kelvin. On the other side of the equation, P2 is what I'm solving for, so I'm going to just leave it as P2. V2 is 15.0 liters. And T2 25 degrees Celsius, I need to turn that into Kelvin. 25 plus 273 is 298 Kelvin. So 298 Kelvin go into that denominator on the right-hand side. I've got all the pieces in place. Now I just need to do my algebra. And this is probably where these kinds of problems get the most difficult, is in dealing with the algebra, especially if that variable happens to be in the denominator of one of these fractions. Because we got to get it out of the denominator before we can do anything else. So I need to isolate P2. Need to get this one by itself. It's already in the numerator, so that's good. What I need to do is multiply everything in its denominator on both sides and divide everything else in its numerator on both sides. So let's see if I can. Okay, learn something new. All that drawing is gone now. All right, let's reconstruct it. So we had half of an atmosphere multiplied by 10.0 liters over 273 Kelvin is equal to P2 times 15 liters and 298 Kelvin. Okay, so we're back to where we started. Now, what I said, we have to get rid of those two terms to get P2 by itself, which means we multiply by everything in that denominator, which would be 298 Kelvin, and we divide by everything in that numerator other than our P2, which would be our 15.0 liters. On this side, all that means is that they cancel. On this side, since I got to do the same thing to both sides, 298 Kelvin over 15.0 liters. My Kelvins cancel and my liters cancel. I'll be left with just atmospheres, which is what I want because I want a pressure unit. And so if I do the calculation, 298 multiplied by 0.5 multiplied by 10 divided by 15 divided by 273 to three significant figures, 0.364 atmospheres is my second pressure. So even though the gas got heated up, the large expansion of that balloon caused the pressure to drop even more considerably than the temperature would have raised it. All right, any questions here? All right, let's do another. I've got compressed gas held at 3.3 atmospheres of pressure and 35 degrees Celsius here in a 5.5 liter vessel. If the vessel were suddenly to expand to 15.2 liters at 55 Celsius, what would the new pressure inside the vessel be? So once again, we got to identify our variables. These look like initial conditions. I'm starting here at 3.33 atmospheres, 35 Celsius, 5.5 liter vessel. So from that, I can derive that my P1 is 3.33 atmospheres. My V1 is 5.5 liters. And my T1 is 35 plus 273 for 308 Kelvin. On the bottom side, I can see that my volume has changed, my temperature has changed. And I'm being asked a question about the pressure. So my new volume is 15.2 liters. My new pressure is unknown. And my new temperature is 55 plus 273 for 328 Kelvin temperature. So I've identified all the variables. I need to put them now into the equation. So again, P1 V1 over T1 is equal to P2 V2 over T2. Using everything that I have, P1 3.33 atmospheres, V1 5.5 liters, T1 308 Kelvin, P2 is unknown, V2 is 15.2 liters, T2 is 328 Kelvin. All right, just like last time, it's the same exact setup. It's the same exact variable we're solving for. I'm going to multiply both sides by the same fraction. And that same fraction is going to be essentially the flip of the other variables next to P2. So 328 Kelvin on the top, 15.2 liters on the bottom, 328 Kelvin on the top, 15.2 liters on the bottom. Everything cancels other than P2 on the right-hand side. Only the units, Kelvin and liters, cancel on the left-hand side. I'm going to be left with atmospheres of pressure, which is good because that's what I need. 328 multiplied by 3.33 multiplied by 5.5 divided by 15.2 and divided by 308 to two significant figures this time. since there are only two in this volume, I get P2 at 1.3 atmospheres. So once again here we see, and this is always going to be the case, large volume expansions are going to have way more impact on pressure than modest temperature changes. And it comes down to that idea of what's going on as far as the temperature is concerned. Since we are using Kelvin, little minute differences in Kelvin temperature are not going to have very large impacts on pressure or volume. Not compared to the size differentials of the containers themselves. All right. Any questions with this practice problem? All right, I want you to try this one on your own. I'm going to come around and check on you, see how you're doing. This is a more of a practical kind of application. Let's say that we have a vessel, and we know that it will break, it will rupture, if the internal pressure exceeds 36 atmospheres of pressure. We've got a gas in a rigid 10-liter canister at a temperature of 25 Celsius and a pressure of 25.9 atmospheres. After being left outside all afternoon, temperature of the gas inside the canister is estimated to be about 75 Celsius. The question is this, it's a simple one. Did the canister rupture due to the increase in pressure? Or would it rupture based upon this increase in temperature and pressure? So go ahead and think about that one. Jot down some ideas. We'll talk about it together in a couple of minutes. So that's the first thing. 36 atmospheres of pressure is a comparison value. It is not one of our pressure values. Second thing we need to think about. If our canister is rigid, what is its volume going to be? Yeah, it's going to be constant. So what we're dealing with here is a situation where we have a constant volume. And we also have these other variables given to us as well. What we are trying to find is that value of P2. We don't know what it is. We're going to compare it at the end against 36 to figure out if the canister is okay or not. But in terms of our combined gas law, one thing that we can look at here is since V1 and V2 are the same, they're both 10.0 liters. They effectively cancel each other out. So this isn't actually technically a combined gas law problem. This is a pressure temperature kind of problem. We can actually reduce this down. The P1 over T1 is equal to P2 over T2. Gay-Lussac's law. To that end, doing that makes this a whole lot easier to calculate. Now, if you had left it in, use the combined gas law, put 10 liters on each side, that would work just fine. In fact, what I often recommend that students do is exactly that. Start with the combined gas law and just plug in everything, and whatever cancels out, it's going to cancel out anyway. But now that I have everything, 25.9 atmospheres, 25 Celsius is 298 Kelvin. '75 Celsius is 348 Kelvin. If I do the calculations, multiplying each side by 348 Kelvin, 348 multiplied by 25.9 divided by 298 to three significant figures gives me 30.2 atmospheres. So to answer the question, did the canister rupture? No. 30.2 is well below 36 atmospheres. So it's fine. And you kind of would hope that would be the case. Most gas tanks need to be able to withstand higher temperatures in the event of a fire or an accident, something else going on. You don't want them to start breaking open as soon as the temperature goes up just a little bit. All right, any questions with this one? I believe it was 10.0 liters. And ultimately, again, that one cancels out. So it wouldn't lay in a it wouldn't have that kind of an effect. That said, yeah, we are giving it to 10.0 there. So it would have been 3 either way. If we had, then yes, you could make that argument, certainly. Any other questions, Adria?
So did you not add the 10 liters for the volume because they're the same?
They're the same on both sides. So it would have come out that we would have had 10.0 liters in my numerator here and in the denominator here when we multiplied. So they would have canceled out then. Okay. So if you find that a variable is constant, you can leave it out of the combined gas law and just recycle with whatever's left. So it doesn't have to be volume. If you find that the whole thing's being done at atmospheric pressure. P1 and P2 are exactly the same. You can leave the pressure units out of the combined gas law and solve with just the volume and temperature. That's the definition of Charles' law. So the combined gas law is a good starting place, but we can simplify it based upon our conditions. So in this case, we had constant volume. We can simplify based on that constant volume. Other questions? All right, let's go back and talk about just one other thing. There is one other gas law worth looking at. It's called Dalton's Law of Partial Pressures. What Dalton's Law of Partial Pressures tells us is that if we have a mixture of gases in a container, the total pressure inside of that container is equal to all of the individual pressures for all the individual gases that make up that mixture. So from that standpoint, when we think of atmospheric pressure, our atmosphere is a combination of a variety of different gases: nitrogen, oxygen, carbon dioxide. Those are the three primary ones. The other ones are present in very, very small amounts by comparison. But what we can look at is the total amount of pressure that is impacting you right now is equal to the amount of nitrogen that's hitting you, plus the amount of oxygen that's hitting you, plus the amount of carbon dioxide, plus all the other trace gases together. Those collectively make the air pressure together. And that's what Dalton's Law of Partial Pressures talks about. Now, there are other applications for Dalton's Law of Partial Pressures. We can talk about things like when reactions occur in water or over water. We can talk about other kinds of things that happen with gases and mixtures of gases. But that's what we're getting at overall, kind of in general. The last thing that I will mention before we let you go for the day is something that kind of circles back to what we talked about at the very beginning, the idea of gas density. If we are at standard temperature and pressure, then we already know that 1 mole of gas is equal to 22.4 liters of volume. Well, we also know from our previous studies that 1 mole of gas has a molar mass. And we find that molar mass on the periodic table. Well, the transitive property would tell us that if the mass is equal to 1 mole and 22.4 liters is equal to 1 mole, then those two are equal to each other as well. And if I put them against each other, divide them by each other, what I end up with is a unit, grams over liters, which for gases is the standard unit of density. Again, grams and liters are used for density because the gas particles are so far apart from each other, as opposed to grams per milliliter, which is what we usually see for solids and liquids. So on Friday, we'll do one example with gas density just to kind of wrap up the chapter. And then we're moving on into chapter 11 to talk about solutions, which should kind of coincide a little bit with what you have been doing in lab this week. So I'll see you then. Have a good day.